So this is going to be a very short video just to set the stage for the next videos on intermolecular forces. I want you to consider two scenarios. The first scenario, scenario A, shows a collection of particles that are at a relatively high temperature, and they're definitely in the gas phase, and you can see they're fairly widely separated and they're moving around like crazy, so it's definitely gas-like behavior. And the objective is to cool it down gradually and see where the gas will make that conversion from gas to liquid through condensation. So step one, we got to extract some of that kinetic energy out of the system, and so we're going to cool it down. And remember, temperature is basically a measure of the average kinetic energy of the system. So if we cool it down and take out some of the kinetic energy, the temperature's going to go down. So when we do that, you can see the particles have slowed down a bit. The temperature has come down. But they're still in the gas phase. They're still zooming around, although not quite as quickly as before. But you can see they're still a gas because they're separated from each other. So we take some more kinetic energy out by cooling it down, and lo and behold, at some point they do condense, and so they start to glom together into these big clumps and then droplets, and then before you know it, you've got a liquid. And as a result of the slower particle motion, the temperature comes down. And whatever point that happens on the temperature scale, that's what we call the boiling point, right? Because that's the transition point between the liquid state and the gas state. Now, let's consider a different compound. This is also in the gas phase. We're at a relatively high temperature again. We do the same exercise. We cool it down, remove kinetic energy, and we find that much sooner in the process we're able to get those molecules to condense and form a liquid. And so therefore the boiling point would be defined right here. And I think you can see we're going to be able to make two statements. So first of all, we can say compound B has a higher boiling point than compound A. And we can make the equivalent statement that compound B condenses at a higher temperature than compound A. Okay, so hopefully this is, I hope this seems fairly straightforward, non-controversial. I'm just trying to set up a simple comparison between two different compounds with their boiling points so that I can pose this question. Why does the compound in scenario B condense at a higher temperature than A? What is it about the compound B that makes it want to stick together in the liquid phase at the higher temperature than compound A? We could frame the question just a little bit differently, and so going from this slide to this slide, what I've done is I simply took my sample of particles in A and I warmed them back up to the same temperature over here that we were with sample B. So what we can say is that the average kinetic energy of these two collections of particles is now the same, okay? But despite the fact that they both have the same amount of kinetic energy, which they have to have, right, because the temperatures are the same, despite this, compound B wants to hang together. It wants to stick together in the liquid phase, but compound A, for some reason, they're just not attracted to each other enough to stick together at that level of kinetic energy, that is, at that temperature. And so this is one of the really important questions that we want to be able to answer with some confidence by the time we're finished with this unit, and that is, at temperature B, what allows compound B to condense while compound A just, is happy to continue on as a gas? So in order to understand how to answer that question, we have to know a lot more about the nature of intermolecular forces. Okay, and so here's how we're going to break it down. We're going to ask, what are they? Are there different types of intermolecular forces? Can we look at a molecule's structure and identify what types of intermolecular forces it can have? So, for example, here's the three-dimensional structure of ethanol. Two carbon atoms. Here are the hydrogens. Here's another hydrogen, oxygen. And if you, we want to get to a point where I can show this molecule to you, and you will be able to tell me all the different types of intermolecular forces that could be occurring if we had a collection of these. And finally, we'll be able to explain the boiling point differences between compounds in terms of their respective intermolecular forces. So really very, very cool, the kinds of things we're going to be able to figure out in a short time. Okay, thank you.